Hello, everybody. Welcome. Here we are in Chapter 8, Section 4, and we'll be talking about polar bonds and molecules. This is the last section in this chapter, and you guys will have your test. Let's talk about the types of covalent bonds. So covalent bonds differ in terms of how the bonded atoms share their electrons, and the character of the molecule depends on the kind and number of atoms joined together. These features, in turn, will determine the molecular properties. So there's two types of covalent bonds. We can have nonpolar and polar covalent bonds, as shown here. The nonpolar covalent bond has an equal sharing of electrons, where the two bonding atoms have similar electronegativities, resulting in a neutral molecule. That is a nonpolar covalent bond. They're usually between identical atoms. And an example is chlorine, chloride with two chlorine atoms, as shown there. Types of covalent bonds, we can have the polar, where there's an unequal sharing of electrons, where one of the atoms has a higher electronegativity, thus having a stronger attraction for the electron. So that would be a polar, where there would be a difference of charge between the two atoms. One atom would be slightly negative and one atom would be slightly positive. So that would be a polar covalent bond. And this is known as a dipole. An example is hydrogen chlorine or hydrochloric acid. So here are types of covalent bonds. Non-polar covalent bonds are completely equal sharing of electrons, and the non-polar covalent bonds have an unequal sharing of electrons. So one end is more negative and one end is more positive. In determining the type of bond formed can be determined by using the electronegativity difference, where if there's zero difference in electronegativity, that would be a nonpolar covalent bond. Even with a very, very slight difference in electronegativity would be still considered nonpolar covalent, whereas the polar covalent bonds would be in this range of difference in electronegativity, whereas when there's a huge difference in electronegativity, that would be classified as an ionic bond. So let's go over an example here. What type of bond is formed between a hydrogen atom and an oxygen atom? So we have a hydrogen and oxygen. We see their electronegativity calculated out for a difference of 1.2. So using the chart, this would be non-polar, polar, or ionic. This 1.2 falls in the polar covalent. The molecules, and lone pairs, which are the non-bonding electrons. And on the bonding polarity, the shape of the molecule, whether it's symmetrical, which means it's the same on all sides, or asymmetrical, meaning it's not the same on all sides. The shape is caused by the VSEPR molecules that we talked, the models that we talked about in the last section, which is the valence shell electron pair repulsion, remembering that valence electrons are arranged as far from one another as possible to minimize the repulsion between them. Polar molecules. So a molecule is polar if it contains polar bonds, is in pairs on the central atom, then the molecule is automatically polar. nonpolar molecules contains only nonpolar bonds, is symmetrical, meaning is the same on all sides. And that would be a nonpolar molecule. An intermolecular attraction, these are the weak forces of attraction between matter of a molecular compound, which is a compound with those covalent ion dipole, 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 the London dispersion force, the intermolecular forces, the ion dipole interaction. This occurs between ion and a polar molecule, and it occurs because there's an electrostatic attraction between the ion and the oppositely charged end of the polar molecule. It's the strongest of the intermolecular forces. Here, intermolecular forces, the dipole interaction occurs between two molecules that are polar, where there is an electrical attraction between the oppositely charged regions of polar molecules. The dipole interactions are similar to, but much weaker than, those ionic bonds. And this is an example of those dipole interactions. The London dispersion forces are the weakest of all the as the number of electrons in a molecule increases. When the moving electrons are on the side of a molecule closest to a neighboring molecule, their electric force will influence the neighboring molecule's electrons to move to the opposite side. So here we have these London dispersion forces in those intermolecular forces, showing a very weak from these unequal distribution of electrons and temporary attraction between the negative and positive ends of these molecules. The London dispersion forces, as you go down group 17, they will increase because the molecules are getting larger. You can see that occurring here. In hydrogen bonding, these are stronger than the London dispersion forces and dipole-dipole interactions, but weaker than the ion-dipole interactions. And these would occur between the hydrogen and one atom and a nitrogen, oxygen, or fluorine on an adjacent atom. And remember, hydrogen bonding is fun because that's how you can remember what hydrogen atoms will bond to a nitrogen, oxygen, or fluorine atom. Kind of a neat way to remember that. Here is a look at these hydrogen bonds, and this is what occurs in water. At room temperature, some compounds are gases, some are liquids, and some are solids. And the physical properties of a compound will depend on the type of bonding it displays, whether it is ionic or covalent. Covalent compounds is mainly because of the widely varying intermolecular attractions and the melting and boiling points of most compounds composed of molecules are low compared with those of ionic compounds. In most solids, for example, formed by molecules, only the weak attractions between the molecules do not melt until the temperature reaches 1,000 degrees Celsius or higher, but most of these are very stable substances, like network solids or network crystals, solids in which all of the atoms are covalently bonded to each other. Melting a network solid would require breaking these covalent bonds throughout the solid. The diamond is an example of a network solid where each carbon atom in a diamond is covalently bonded to 4 other carbons, interconnecting the carbon atoms throughout the diamond. So diamond does not melt. Rather, it becomes vaporized to a gas at 3,500 degrees Celsius and above. So that's an example of that high temperature. These are the characteristics of ionic, and study it going through the different representative units, the bond formation, type, water, and then their electrical conductivity of an aqueous solution. That's the end of this section. Let me